So he was just surgery the day before, but our finals are not stop. Our class Monday, so it's always fail.
So guys, I will say this much, everybody, even guys and girls and everybody, all the organic entities in this room at the moment. And then somebody's gonna complain. He's discriminating against us non-carbon-based life form. Oh shit! Didn't know. All right, guys. So we have a standard normal distribution, right? Standard normal distribution. Say hello to it. Don't feel bad if it doesn't say nothing back. It's just ink on the board. So if it does say something back, take some meds. We have things that are in the real world that kind of follow this pattern, and we can kind of put them into this shape and through this formula, right? So I calculate from a raw data point standpoint, I can convert it into a z-score, compare it to this chart, and get areas, for example, from the z-score chart. Everybody's still kind of... All right. So there's also... Now you shouldn't be freaked out to realize, I mean, we already talked about the t distribution, but that really looks a lot like this distribution, just all the values are a little bit bigger than they normally would be. It really kind of looks the same. This is the first one that looks very different. And it actually looks very different, even more different than that, depending on how big the sample is. The smallest that it could be is 0. And the biggest it could be is theoretically unbounded. So just go forever. And what it is, it's too bad we didn't have enough time to get into it. I'm sure you're not going to lose a lot of time crying over this fact. But standard deviations really play a huge part with it. This is how standard deviations would be distributed. That's the real usefulness of this. What kind of tells me the shape of this, if it's going to be skinny or fat, is the what? Standard deviation. So if I want to see what do standard deviations themselves look like when I graph them, can you realize that's a little bit funky? Well, they're going to follow a different distribution. They actually follow this one. It's called the chi-square. This is one symbol, chi-square. It's called chi-square because it's sort of like folding the z table on itself. So it's like squaring the z values if you fold them on top of themselves. Like it's freaky. So don't try to square root this stuff. That's a part of the notation. You guys kind of with me there a little bit? All right. Maybe. So, sample standard deviations can get pretty large. They're kind of centered around the population standard deviation. So that's basically the shape of it. What we're going to use it for, something related to this, is this calculation here. Oh, shit. If you weren't here last time, I'm not sure what to tell you. Oops, that's a big sum. Did I put it on the... Oh, good. All right. So you can read it a little better. It's on the little handout. So we're going to do an example problem. We also have to look at how to read this chart. So I think first we'll just look at how to read this chart by itself. And then we'll try a problem out. Ooh. All right. So say I had n of, what you got, Jeff? 18. And the test we're going to use this for is called a goodness of fit. You just got to love that name. And the idea is, if I'm at 0, that means that the two things I'm looking at are exactly matched up. They're exactly the same. And the minute they're not the same in some way, it's going to go away from 0. So if you were here the other day, hopefully this made kind of sense, and you realize now that it's not the full hypothesis test, it's just the easiest part of the concept of hypothesis test, which is I've got to set up what far enough away from 0 is to show me that there is a difference between these two things that I'm looking at. So that sounds very familiar, hopefully. And not remarkably, we call this thing chi-square critical, I think is what the book calls it. Depends on which book you use. Crit, exactly. Yes. However, whatever you want to do with that word, you can do it. So what are the degrees of freedom in this case? And by the way, this is 18 categories. Like yesterday, last time we did an example with, did we do an example with A, B, C, D, F, right? So there were 5 categories. So this is 18 categories. So, I don't know. Maybe the 18 holes in a golf course. I don't know. I don't even play golf. I don't know why that came to mind. So what's the degrees of freedom going to be? Thank God it's the same thing we always say. 17. And let's say that I want to use a level of significance of 0.01. Sure. So when I drew this here, where's the tail that I created? Up here. And notice, to the right. And notice what it says on the chart, area to the right of the critical value. Well, how much area is there going to be in here? I just told you. How much area is in here? 0.01. I like it. So for these goodness of fit tests, whatever the level of significance is, that's what you're going to look up to find your critical, to see what far enough away is. So for this example, I've got 0.01. I got a degrees of freedom of 17. So just bring those guys together, and we get 33.49. All right, I like it. So that's level number 1 is, are you able to use the chart? Level number 2 is, how the hell do you use that damn formula? Right. You guys? Now, to be honest, real quick, I just can't stop myself, so too bad for you. The real full-blown power of this is I can make confidence intervals for standard deviations themselves. So I get a sample standard deviation. I'm curious. I want to be 95% confident that the real standard deviation is between this and this. You guys, that sounds very familiar, right? We just never done it with freaking standard deviations before because we didn't know what they looked like when you graphed them. But now we do. So I could do this, and then I would get these 2 chi-square scores that I have to look up and put it in this formula and blah, blah, blah. So the most important thing to me, the reason why I can let go of some of this is because just showing you the chi-square table, telling you a little bit about what it does. Now, if you go into psychology or something else, some business that uses this, it should be pretty easy to kind of merge what we've already done with confidence intervals together with this chi-square stuff. It's the same stuff. It's exactly the same stuff, believe it or not, just using a different table. All right, so let's come back to a problem we'd actually see. So let's do this. Let me make one up, see what happens. There it is. So let's do one with percentages, because that's the one that's got a little more work to it. When they just give you the numbers that you expect, that's great. But let's do one with the percentages, because you know that's the one I'm going to give you a test or something. Let me actually do one right out of the book here. So here's marital status. For men age 15 and older, so never married, we expect 31.3%. Married, I expect 56.1%. Widowed, 2.5%. And divorced or separated, 10.1%. Okay. So one good thing to check out is, do they add up to be 100%? Thank God they do. So let's say I take a sample of 400 men, U.S. men, 15 and older. How many of them would I expect to have never been married? How do I calculate that? Yeah, 31.3% of any group I expect to be have never been married. So 31.3% of 400. $125.2.
Yeah.
All right, is everybody with that? You guys see where that comes from? Everybody freaks out when they get percentages. You got to create your own expected number of whatever. Right? Expected number of brown M&Ms, expected number of grades of B, expected people that have never been married. Yes?
So 400 wouldn't be N?
No. In fact, what's N here? I'm glad you said that. I was going to get to it later, but we might as well say it. Yeah, N is 4. Good. There's 4 categories. So how did I get that? I took, there's 400 men. I'm looking at the 31.3% of 400, right? 0.313 times 400. And that's where I got the 125.2. Why are we okay with the 0.2? Is there a 0.2 dude? No, because that number is an, what do you think? Expected value. It's an average. So averages could have anything. I don't care. You have 2.8 kids. You're like, I don't want to see that 0.8 kid. No, there's no 0.8 kids. It's an average. So what do I get here? Somebody help me out. 24.4?
Yeah.
10. I like it. And then 10.1%? 40.4. Now, what's another level of check you can make? What do you think should happen that I could check right now to make sure that I didn't put something weird in the calculator? Yeah, they got to add to be 400. Somebody help me out. They do, it seems like. All right, I like it. She's like, let's just get this going, man. All right, I understand. I'll stop typing on my hand. So everybody's got that handout from last time. So I kind of set it up for you to show you how this works. So next to it, I'm going to put observe. So here's, bless you, bless you, bless you. That's money right there. Oh, we ran out. Ramsey's ran out of blessings, man. It's terrible. The rest of his life, he's like, sorry. Now let me show you. Here's what they tell me was the observations that were made. We saw 140 of these people. We saw 238 of these people. We saw 2 of these people. And we saw 20 of those people. Now, I mean, just eyeballing that, would you say that that looks pretty close?
Yeah.
Yes. But it's the same kind of thing like when we said we think the average is more than 3.19, and we take a sample, we get an average of 3.3. That seems pretty good, but we don't freaking know how far away it is until we do the whole test. Okay, maybe. So let me see what they tell me. Where they tell me, well, screw them. I'm going to make up my own thing because they don't tell me. All right. So let's say we want a level of significance of 0.005. Does it go that far down? Hopefully.
Yeah.
Yes, cool. I like it. What's my degrees of freedom? 3. I like it. So what's my critical score going to be? So right now I'm kind of doing step 3 of hypothesis test. I'm setting up the rejection region right now. Yeah, 12.838. You guys see that? So if I made you, and I won't, I figure you've gone through it enough. Okay, if chi-squared star is what we kind of settled on calling it last time, is greater than that, then we can reject that they're the same. Right? 0 means they're the same. So if it's at least this far away, or more than that far away, then they can't be the same. It's just so freaking far away. Okay. So now I'm going to calculate. So this is like setting up the rejection region. And then I'm going to calculate where we actually fell. Did we fall that far away? Where did we fall? And I'm going to do that with that formula, this guy here. always put that up there, yeah. Big ass sum. So now, hopefully we've gone through this enough earlier in the semester and throughout that you can see, and if you can't, you can see it on the handout, what columns I need to make. I've already got my observed. I've got my expected. Now I just have to take the difference and square that, and then divide by the expected. Now, to be honest, you can do all of that in one thing. Let me show you guys, let me remind you guys how to do this in your calculator, if you want to. So in here I can put, here's the expected, 125.2, 24.4, 10, 40.4. Over here I put the observed, 140, 238, 2 and 20. Now let's see if you guys can handle this. I'm going to put the whole damn thing, I'm going to put that into L3, so then I can just sum L3 and get what the chi-square is. So I want to do observed, which is L2. To be honest, it really doesn't matter which order you put O and E in there because it's squared. But let's just do it straight up. Observed minus expected, that's in L1. Does everybody see what's happening? Is that cool? Here's L1. Here's L2. Oh, you should probably be looking that way. Right? L1, L2, so I'm going to do L2 minus L1 squared. And then I'm going to divide that by, what's the formula say? Yeah, by the expected, which is in L1. I like it. Now, do you have to use a calculator for this? No. You can do this by hand. I'm not going to give you one with a crazy amount of categories. Oh, that's good, Jeff. So, let me see. What mistake did I make? Learning moment for all of us. Yeah, I'm trying to put a whole list into one spot. That's good, Jeff. So when you get that data type argument or data argument, I can't remember exactly what it said. You're trying to put a whole list into one spot. So I was supposed to go up to L3 and then say, all right, that's L2 minus L1 squared divided by my expected, which is in L1. Okay. This should feel very familiar. This is sort of like when we did standard deviations. You guys getting those same numbers if you're playing along? If you did it by hand, you could just do it by hand, get the same numbers. And now I can just add those numbers up. I don't know if you remember this, but you can go to list sum. Where was it now? I forgot. 1, 2, L3. Yeah, L3. What's this stuff over here? Got it. You get 19.27? Yes? Yes. All right. Huh? All right, you guys still with me here? How does it? Where do we fall? Yes, sir.
Where's sum again? Sum.
You go to second stats, go to list, do math, and then number 5 is sum. To be honest, some of you guys should be able to handle this. Some people always look at the wrong thing, but if you just go to stat, calc, one var stats on L4, no, what was it, L3. The only thing I care about here is the sum. Same sum, see? But everybody gets freaked out about all the other shit it gives you. Right? It's just like, if you need it, here's all. No, I don't need it. Just want that sum. So, did we make it far enough away? So, what does that mean? It's evidence that it's different. That did not follow what I expected. Not close enough. Maybe. That's really all there is to it. So it's a question of, can you use the chart correctly? And can you use the formula correctly? So let's do this. Let me make one up for you to try on your own. So we're going to one from here, from this stuff. Oh boy, here we go. Make one up here. Alright guys, somebody help me out. Make sure that adds up to be, let's see, 49, 84, 93, 100. Okay. Let's say I look at, so this is looking at people in a relationship and how many children they've had. And let's say I look at 350 couples. 350 couples, right? So this is what I expect to happen. Sorry with me? So 350 couples looked at. And we observe this. We observe, what you got, Jeff? Oh no, man. Make it up like always, buddy. Uh-oh. 1959. I think that adds up, hopefully. Is everybody with me? Sorry, it took a little while. Too bad. Now I want you to do everything we just did using alpha equal to 0.05. Yeah, to make sure everybody's on the right first step. You definitely don't want to use these with those, right? How do I figure out what goes here? I got 350 people. So 21% of them should be having no kids, so forth. You guys see that? Same thing we just did.
Oh, that's not.
$7.35. Just make sure everybody's on the right track. What number is actually this spot? 73.5? Right, 21% of 350. Okay, keep going.